Hi folks. In this lesson, we're going to learn how to model quantities using ratios. So kind of using fractions to set up and model problems. A ratio is just a comparison of two quantities. It's often written as a fraction. It doesn't have to be, but that's the method we're going to be using today. A proportional relationship, which is sometimes just called a proportion, but a proportional relationship is an equation that shows two ratios are equivalent. For instance, hopefully you all know that 2/8 means the same thing as 1/4, so that's a proportion. Those are equivalent ratios. We're also going to look at using a ratio specifically to relate two quantities that have different units. Rates are important in lots of things like speed, miles per hour. You can see that miles is in the numerator, hours is in the denominator, so that can give us a speed. Or it could be some sort of ratio that comes out of a recipe, like 4 cups of flour makes 1 loaf of bread. Um, so a rate is just any ratio that specifically has two different units in the numerator and denominator. The first example of ratio problems that we're going to look at are setting up a proportional relationship using shadow problems. So if you are 6 feet tall and you cast an 8-foot shadow, then yourself and your shadow, the kind of fraction created, the division problem created by your own height and your shadow, is going to be proportional to any other object with its shadow at the same time of day. If you wait an hour later, your shadow is going to be a different length. But at the exact same time of day, this ratio is going to be equivalent to the ratio between the tree and the tree shadow. Okay. So this is a proportional relationship that we can set up. So we basically, using the numbers, 6 feet tall with an 8-foot shadow. The tree, I don't know how big the tree is, so I'm going to just use the letter T to represent the tree, but I know that its shadow is 30 feet long. It's very easy for me to measure a shadow on the ground. So what is the height of the tree? Well, I can use the skills that we learned in the last couple sections to get T all by itself on one side of the equation so that I can solve this problem. So it's always best to simplify what you have on one side of the equation first. So this is 0.75. 6 divided by 8 is 0.75. Is T divided by 30. And now to get T all by itself, I need to get rid of the 30 that's in the numerator by multiplying by 30. I'm going to do that to both sides, multiply by 30, and I get that T equals 22.5. And of course, this is a story problem. This number needs units with it. The height of the tree is 22.5 feet. I'm going back to check your answer. See if it makes sense. 6 over 8 is 0.75, so hopefully 22.5 divided by 30 is 0.75, and that does turn out to be true. Let's look at another example where we might use a ratio, in this case, rates. This says, so this is just a big table of statistics for a baseball pitcher, and they want us to use rates to compare the pitcher's performance in 2019 to his performance in 2020. So comparing those numbers to those numbers. And they suggest using strikeouts per walk. Well, strikeouts per walk just means strikeouts are in the numerator and walks are in the denominator, and we want to compare the 2019 number to the 2020 number. So 2019 strikeouts are 100, walks are 29, so 100 over 29, and that is, on your calculator, that's 3.448, so I'm going to round that off to 3.45. And then for 2020, I'm going to use the numbers 73 and 20. So 73 over 20 is, punching that into my calculator, is 3.65. So in terms of strikeouts, which are a good thing, and walks, which are a bad thing, good thing on top, bad thing on bottom. So it looks like this pitcher did better in 2020. They had more strikeouts per in 2020. Let's use a different statistic this time. Let's use earned runs per inning. So earned runs are going to be on top and innings are going to be on the bottom. And again, we're comparing 2019 to 2020. Earned runs are 19 and innings are 70. So 19 over 70 for 2019. And 19 divided by 70 is about, if you round it off, 0.27. And if we look at 2020, I'm going to use earned runs of 15 and innings of 50. So 15 divided by 50 is 0.3. And so it looks like there were fewer earned runs per inning in 2019 based off of that information. So really, you could have chosen any of these statistics to have in your numerator and any of these statistics to have in your denominator, but those were the ones asked for in the question. Okay. By the way, these are called unit rates, like this 0.27. That's the unit rate for earned runs per inning. Any ratio can be calculated plugged into a calculator to find out what the unit rate is. Let's look at another way we can use ratios. Ratios can be used as conversion factors to help convert from one set of units to another. For instance, if we're asked to convert 4.8 gallons to fluid ounces, I don't know how many fluid ounces are in a gallon, but I do know there are 16 cups in 1 gallon, and then there are 8 fluid ounces in 1 cup. So what I can do is I can take my 4.8 gallons and I can multiply by one of these conversion factors. 16 cups equals 1 gallon. Because this, if I set it up as a ratio, makes a fraction that's equal to 1. For instance, if I write 16 cups over 1 gallon, even though the numbers don't make the fraction look like it's equal to 1, those two things are equal to each other. So the units make the fraction equal to 1. Units in this type of problem are extremely important. Now, another conversion factor that you could use in a different type of problem would be to flip that fraction, to write 1 gallon is the same as 16 cups. However, I'm not going to use this particular conversion factor in this problem because I need to set up my conversion factor so that the units that I start with get canceled out. I want gallons to be divided away so that gallons disappear because I don't want to have gallons in my final answer. I only want to have fluid ounces in my final answer. So far, I've only used one conversion factor. So I've converted to cups. I haven't yet converted all the way to fluid ounces, which is what I want my final answer to be. So I need to use a second conversion factor. 8 fluid ounces equals 1 cup. Again, I've got a choice. I can either write 8 fluid ounces equals 1 cup, or I can write 1 cup equals 8 fluid ounces. I want to choose the conversion factor that's going to get rid of the units that I don't want to see in my final answer. So I'm going to choose this version. I want to get rid of cups by dividing them away. 8 fluid ounces is the same as 1 cup. I want to divide the cups away so that I only have fluid ounces left in my final answer. Looking at this math problem, I multiplied by a fraction that means 1, and I multiplied by another fraction that means 1. So this expression, I'm going to end up with a number that isn't 4.8 gallons anymore, but it means the exact same thing as 4.8 gallons, just in fluid ounces instead, because the gallon units got divided away and the cups got divided away. So the math that I'm left with to do is 4.8 times 16 times 8 divided by 1 divided by 1. And if I punch all that into my calculator, I end up with 614.4 fluid ounces. Now, sometimes students insist on doing these problems. It's like they have an idea in their head, like they know that gallons are big and fluid ounces are small, and they insist on deciding whether to multiply or divide based off of their own knowledge of the units. And while that's a great way to check your answer, eventually in a science class, you're going to come across units that you are less familiar with. And so it helps to have a strategy like this that always works, so that when you're faced with unfamiliar units, you can still do the math and you aren't just totally stuck because you don't know what to do. This method always works no matter what units you are dealing with. So, for instance, if your friend says they're about 454 million seconds old, how old are they? Well, I don't know how many seconds are in a year, but there are some other conversion factors that I do know. I do know that there are 365 days in 1 year. I know that there are 24 hours in a day. I know that there are 60 minutes in an hour. And I know that there are 60 seconds in 1 minute. So if I take that 454 million number, and those are seconds, I can come up with some conversion factors to uh, get rid of seconds. And I can't go to years in one step because I don't know how many seconds are in a year, but I can use a series of conversion factors to convert um, to years. So I'm going to get rid of seconds and go to minutes because I've got a conversion factor that will do that for me. I'm going to get rid of seconds. There are 60 seconds in 1 minute. And then I'm going to go from minutes to hours. There are 60 minutes in 1 hour. And then there are 24 hours in 1 day. And then, then there are 365 days in 1 year. And if you look at what happens with the units here, the seconds divide away, the minutes divide away, the hours divide away, the days divide away, and my final answer is in terms of years. Now, if you punch this in your calculator, you'll get a big long decimal, like 14.396 something. Our number just had 3 kind of non-zero digits in it. They didn't say they were exactly 454,226,422 seconds old. They rounded it off. And so we need to round off our answer also to 3 kind of non-zero digits here. So I'm going to round this off to 14.4 years old. And that is my final answer. So let's look at how kind of modeling real life and using this same strategy for conversion factors. So wind speeds on Jupiter can reach 180 meters per second. Wind speeds on Neptune can reach 1,200 miles per hour. Which planet has faster winds? Well, we can see that these units are different. So I have to take one set of units and convert it to the other planet. So what I'm going to do is I'm going to take Neptune's I'm going to focus on Neptune and change Neptunes into meters per second. So I'm going to start with 1,200 miles in 1 hour. Notice this time I'm starting with a rate, miles per hour. So I need to write this as a division problem, as a fraction. And then when I want to convert units, I need to convert from miles to meters, and I need to convert from hours to seconds. Okay, so it's not just the miles that needs to be converted. It's not just the hours that need to be converted. It's both. So let's focus on doing the miles to meters first. Okay, so here are a couple of conversion factors that are going to help us. I want to get rid of miles and go to feet, and then I can get rid of feet and go to meters. So I'm going to get rid of miles. There's 1 mile is 5,280 feet. And then there are 3.28 feet in 1 meter. So if you look at what's happened with the units so far, I got rid of miles, I got rid of feet, I have meters, just like I want to have in the final answer, but I still have hours down here, and I don't want to have meters per hour, I want to have meters per second. So let's focus now on converting those hours to seconds. We know from this problem up here that there are 60 minutes in 1 hour. There are 60 minutes in 1 hour. Now notice how I've set this fraction up. This time hours was in the denominator. I want to get rid of what's in the denominator by multiplying by hours. And I want new units in the denominator. First minutes, and then in the next step we want to go to seconds. Okay. So if you were dividing by units that you want to change, you need to multiply them away. If you were multiplying by units that you want to change, you need to divide them away. The last conversion factor that we need is we need to know that there are 60 seconds in 1 minute, and then those minutes cancel out and we're left with seconds, just like we're supposed to have. This is one big 5-part multiplication problem. But if we do 1,200 times 5,280 times 1 times 1 times 1, divided by 1, divided by 1, divided by 3.28, divided by 60, divided by 60, you will get as your answer on your calculator 536.585 meters per second. But let's be sensible. We started with just a couple not even 3 non-zero numbers in our value. So rounding this off to about 537 meters per second is a more reasonable place to round off this value. Wind speeds on Jupiter reach 180 meters per second, but on Neptune's wind speeds can reach 537 meters per second. So Neptune's wind speeds are much faster. Just as kind of an explanation of why these conversion factors work. Okay. Just remember that units can be multiplied and divided just like numbers. Meters times meters is meters squared. Meters cubed divided by meters is meters squared. Miles divided by hours gives you miles per hour. Conversion factors are just ratios that change from one unit to another. The top and the bottom are equal to each other. Those 1001 don't look equal to each other, but because of those units, they are equal to each other. Remember, all conversion factors can be written 2 different ways, depending on which units you put on top and which units you put on bottom. But only one way is correct for a given problem. You always want to make sure that you get rid of the units you start with and you convert to the units you want to see in your final answer. Okay. So hopefully that understands a bit behind why conversion factors work. I promise you, you'll see this in chemistry class when you take chemistry and physics as well. So it's more helpful, even if you think you can do the conversion in your head, because maybe it's just one step, it is worthwhile to learn this step-by-step process. I hope this helped.